So now we come to the topic about how to define the attribute of the stress. And stress has two types. One is called the normal stress, one is called the strain stress. And the normal stress basically is induced by, like this, the direction of the loading is normal to the cross sections we choose. So this is called the normal loading. The normal loading will induce the normal stress. And by definition, magnitude equal to the magnitude of the loading divided by the cross-sectional area we pick. And in normal stress, we have further two types of the normal stress. And for this case, you can see basically this material has been suffering by pulling away by stretching. So the induced stress is called the, we call it tensor. So if we have material like this, and it's under the stretching out, so the induced stress will be something like this. Basically, it's pulling out. So this is called the tensile stress. And tensile stress in our sign convention is we define as a positive. And compared to the tensile loading, we have the compressive loading. And again, this loading is normal to the cross section. And this loading is trying to compress the material. So for this case, that will induce the compressive stress. So this is called the compressive stress. And in our sign convention, we use a negative for compressive stress. So in your calculations, to express stress, you need three quantities. One is the magnitude. The second one, you need to give the appropriate unit. The third one, you need to indicate whether the stress is tensile or compressive. Okay, so for the complete expression, you must have in your answer, you must have the three attributes being described. Okay, and that is about the normal stress. The second type of the stress is called the called the strain stress. The strain stress, we can utilize this model for example here. Basically, you can see this here. This figure is a little bit tricky, but you can see this figure is P applied to this one, normal to this cross section, but that is not our interest. Our interest in this model is about this cross section here. Okay, and you say, why not? Can we choose a cross section like here? Yes, you could, but that is not our interest in explaining the concept here. So in particular, let me pick this cross section. So once I pick this cross section, I simply do the free body diagram to expose, to keep this portion. So this is the cross section we expose. Okay, we pick this cross section, and then you can see by equilibrium, then on this cross section we must have a reaction to be counterbalanced with this one. Otherwise, this block will keep rotating. That in our in our mechanical material, we study statics. Okay. So this is the induced the reaction force in this cross section. And now we come to our key concept. You can see this reaction force is parallel to the cross section, which is our interest. So as long as any internal force or reaction force is parallel to the cross section, then this force will induce the strain stress. That is pertaining to our original definitions. So let me draw the strain stress here. So let me draw that kind of the free body diagram. So this is our material, and here we have two pairs of the force. Let me call them P and P. And again, in particular, I'm interested in what's going on in these cross sections. So I pick the free body diagram there, and then this is a free body diagram, and I use the green dashed line to indicate the cross sections we are interested. So now this is our loading we are given here. On this cross section, we must have the balance. So that means we keep using the force in the vertical direction equal to 0. We found on this cross section, we must have the same magnitude of the force, and this is P and pointing downward. So this one will be equivalent to, in terms of our stress, then that stress can be drawn like this. So this is our cross section, and basically the stress, we can represent it by this. The stress, this stress is induced by this loading. This loading is parallel to the cross section. So here we found this is the shear stress. Okay, for shear stress, we use the tau as the common symbols in our textbook. For the normal stress, we're using sigma. Okay, that is our symbol conventions. So using tau, so tau basically again equal to P divided by cross-sectional area A. And the same thing for this case, let me call this is P. This one will be equal to P divided by cross-sectional A. So from here you can see it really doesn't matter that is the normal stress or shear stress. The calculation of the magnitude is always the same. You simply divide the magnitude by the cross-sectional area. But somehow here you can see their directions is different. The normal stress is normal to the cross-sectional area. The shear stress that is parallel basically is flowing onto the surface of the cross-sectional area. Okay. Any questions? So we stop here.
When we express the stress for the tensile and compression, can we just use the signs, or do they need like a C or a T?
For this one?
For when we express the stress right
one.
here?
Okay, so let me give one example here. So here we can continue recording this one. So for example, let me say this area A equal to say 10 meter square. Okay, say P equal to say let me say this is let me 10 to the minus 2 meters square. This is this newtons. Okay, so for this case, the stress will be equal to P is 1,000 newtons divided by area 10 to the minus 2 meter square. So basically this is 10.6 Newton meter square. This is 1 MPa. Because this is our calculation of the magnitude, and this is our physical applications. By observation, this is tensile. So in your expressions, this you can say this is tensile, and you simply added up this one by your observation of the problem you are dealing with. Okay, or sometimes you like, as you can say, it's positive 1 MPa. Using positive is to cope with our sign convention.
Okay.
Okay, and for this case, the same thing, the same area, the same magnitude, so the stress will be equal to, in calculation, is 1 MPa. And because we observe this is compressive, so you have to write it up compressive. Or you can write it up as minus 1 MPa. So in the very last step, we artificially added up the attribute tensile or compressive by writing or by giving an appropriate sign. This sign won't appear from your calculation procedures. This sign is given by our observation. Got it? Okay, good. So that is for this topic.